So I want to get started doing a few examples of vectors and trigonometry and how we use that. Um, we use the same math all year. So we use some equations, sure, which is some algebra. But in terms of vector resolution, it really is the same math all year for things, whether you're using forces or acceleration or velocity or things like that. So hopefully you've had some of this in geometry class or algebra 2, and if not, it won't be so much a review, but there's some really good resources on Physics Classroom. So if you recall, I'll go to Physics Classroom right now, and it's going to tell me I need to log in with weird stuff because our district's being weird. So I've got to identify boats. That's maybe part of a boat. That's it. Also boats. I think that's it. Hopefully they know that. So anyhow, when you go here to the Physics Classroom tutorial, which is really kind of their online textbook, vectors and motion and forces in 2 dimensions, I asked you to read several of these sections. There's some other good sections as well, like riverboat problems, vector resolution, things like that. They talk about things. I don't like this diagram. It looks like they're choking the dog. That's not cool. At any rate, they have some pretty good examples. And if I go back to this, about vector addition, for example, they show you here how to do things, Pythagorean Theorem, with some geometry, things like this. It's a pretty good geometry review. So I would strongly recommend going back and looking at some of those sections if you didn't do that very well before. So at any rate, I usually start off with asking 3 plus 4 equals, and most people will say 7. And the reason they say 7 is because that makes sense if they're going in a straight line. Well, if you add things vectorially, if they're going in the exact same direction, then 3 plus 4 do equal 7. If they're going in the opposite directions, 3 plus 4 would basically be subtracting off the 4, and that would equal 1 in a certain direction. If they're at right angles, 3 plus 4 equals 5 due to the Pythagorean theorem. But if you have 3 plus 4 and they're at anything other than a right angle, or with each other, or against each other, then we have to use a little more trig to get that answer. So a little more trigonometry. So a lot of times we use vector quantities, and those are ones which have both a magnitude and a direction. Scalar quantities are those that only have a magnitude. For example, velocity is a vector quantity, speed is a scalar quantity. If I tell you something is going 45 meters per second, that's a speed. But if I said something like 38 miles per hour due east, that's a speed, which is a magnitude, and which is the 38 miles per hour, which is the amount of speed, and the direction was due east. So this would be a vector. Other examples of vector quantities include things like acceleration and force and displacement. We'll use velocity. I said there'll be some other things with momentum later in the year. And we need a standardized coordinate system for this. So in math, I think a lot of times they start with 0 degrees here to the right and go counterclockwise to 360 degrees. Physics uses the same coordinate system that everyone other than math teachers, I think, on Earth uses, which is a polar coordinate system. Meaning, if you think about the North Pole, it is at 0 degrees or 360 degrees. Then we can go around to the right. East is 90 degrees, south is 180 degrees, west is 270 degrees, and we get back to 360 degrees. However, we can actually use some other methods to figure out the direction of things, because going up to 360 can be kind of difficult. So if we want to add vectors acting on an object at the same time in the same location, which is called concurrently acting vectors, we can do so a few ways. One is we could add vectors vectorially by drawing them tip to tail. So the result of adding vectors can be found by looking at the tail of the first vector and attaching it to the arrow tip of the last vector. So you definitely will need to know how to use things with Pythagorean Theorem, trigonometry, and your calculator in this topic, by the way. And make sure that your calculator, if it's a graphing calculator, is in degree mode. Many math teachers have you defaulted to radian mode, and that'll be very confusing. The other thing we do is we tend to think of examples as being from north or from east or from south or from west. So we're measuring in a quadrant, like the southwest quadrant or the northwest quadrant. And we'll talk about that a little bit. So here's my first example with a vector. If I have 3 meters going to the east and 4 meters going to the east, we simply add those. We would get 7 meters to the east. If we have 3 meters going to the east, 4 meters going to the west, I put my arrows tip to tail, so that's what I did here. Arrow tail to arrow tip, tail to tip. The resultant is from the tail of the first one, which is the 3, to the arrow tip of the last one, which is the 4. So that resultant is 7 meters to the east. For the second example, when they're going opposite directions, notice I've got my 3 meters going to the east tail, but the 4 meters, the tail of it is again pointing back to the left, or west. So it's still tip to tail, but my resultant is from the tail of the first vector, that's the 3, to the arrow tip of the last vector, which is the 4. So now you can see that the resultant is pointing to the west, or left, and that is would be a resultant of 1 meter west. Okay, let's look at one where we've got things at 90-degree angle. Let's say we have 3 meters to the north, and then we move 4 meters to the east. What will be our resultant? We can find the magnitude of this resultant by using the Pythagorean theorem, which is a squared plus b squared equals c squared, or some derivation of that. So when I do that, I get 5, which would be 5 meters. Now to get this angle, if I want to find an angle, I need to use the sides of the triangle. Opposite over hypotenuse would be the tangent of that angle. So 4/3 is equal to the tangent of this angle. So if I want to find the angle, I don't need to use the tangent function, I need to use the inverse tangent function. So the tangent function uses an angle to help you figure out side or hypotenuse lengths. The inverse trig functions help you use those side or hypotenuse lengths to figure out the angle. Because for any given triangle, if you have a ratio of 4 on the opposite side to 3 on the adjacent side, it will always mean the same thing. Whether you have a big triangle or a small triangle, if you have that 4 to 3 ratio, you'll always be at the same angle. So in this case, I use an inverse tangent of 4 divided by 3, which gives me 53 degrees. Now let's say I drew this a little differently. Let's say I drew the 4 meter arrow first and the 3 meter arrow last. When I do that to connect to and get a resultant, and I'm doing that in green here instead of the brownish color, my magnitude is the same, still 5 meters. But now 3 meters is my opposite side and 4 meters is my adjacent side. So if I take inverse tangent of 3/4, I get 37 degrees. That's a different number. So what we need to realize is that these are angles measuring from different axes. So whatever is your adjacent axis that is either horizontal or vertical, that is going to be the side at which you're moving from. So in this case, I've got a vertical axis that's going up, so that's north. So when I get this angle, it's going to be from north, because that's the direction I started. Here, I start out to the east and then go north, so my adjacent side of my triangle is east. So whatever angle I get is going to be from east. So in this case, when I look at this and I get a 53-degree angle, I'm going from north, but I'm going east from north, or east of north. So my final resultant for this is 5 meters at 53 degrees east of north. This one would be 5 meters at 37 degrees north of east. Well, those mean the same thing. They point in the same direction. So it doesn't particularly matter which way you do this, but you've got to show me your work when you're doing things on a quiz or you're submitting work online, so I know that you understand what you're doing and that we really do mean the same direction. So in this case now, we can always record things from north, which is 0 to 360 degrees, which is what I showed you up here. So technically, if I'm this, which is 53 degrees from north, east of north, I could just say 53 degrees. Most people don't like that once you get beyond that northeast quadrant because you have angles between 90 and 360 degrees, which can be kind of confusing. So this talks about the interior angles or the adjacent angles being the frame of reference. And that's what I talked about above. Well, now, what if we want to counteract multiple forces, let's say? So let's say we're talking about a force vector, and we want to apply a single force on that object to counteract it. So for example, let's say there's a bunch of people pulling on something in all different directions. We couldn't just add their forces up if they're pulling in all different directions. We'd have to get a resultant. So the resultant force would be adding vectorially all those forces in different directions. Well, if we want just one force to counteract that resultant force, it would be the same magnitude or size as the resultant, but in exactly the opposite direction. So this counteracting force is called an equilibrant force. Sometimes I call it equilibrant. I don't know why I want to verbally put an I in there, but I think it's called an equilibrant force. And again, if you go online and look it up, it talks about being able to bring something into equilibrium or balance, which is exactly what an equilibrant force does. So I usually do an example with a chair or something being pulled by multiple people or someone being pulled by ropes. We probably won't be doing that this year. And then one extra force would act to cancel those out. So an equilibrant force cancels out all those other forces. The idea of vector resolution is to break forces down into their vertical and horizontal components and then add those parts back together. That kind of got cut off there at the bottom of the sheet. So we're taking a bunch of vectors, we're breaking them into their horizontal and vertical components, we're adding all the horizontal components together, or subtracting them if they're pointing opposite, and we're adding all the vertical components together, or subtracting them if they're pointing in opposite direction. And then we get the total amount north or south, and we get the total amount east or west, and we draw a final triangle to get our final resultant. And that sounds like a lot of work, but honestly, once you get used to it, it's the same routine over and over. So here's sample one. I thought I did sample one before. That was example one. Oh well. So at this point, you have a 15 Newton force pulling an object due east, and a 20 Newton force acting concurrently, so at the same time, pushing due north. So I draw these tip to tail, even though I know they're acting at the same point, because that's going to give me a triangle and allow me to mathematically and graphically perform vector resolution. So if I want to find the resultant and then the equilibrant, always, always, always draw a picture. It helps so much in physics to draw pictures. So in this case, I've got 15 newtons east, 20 newtons north. I use the Pythagorean Theorem to get my resultant of 25 newtons. And then since the tangent of the angle is the opposite side, which is 20, over the adjacent side, which is 15, I use the inverse tangent to get that angle. And once again, that's about 53 degrees. That's similar to the example I had earlier. So the resultant would be at 25 newtons at 53 degrees north of east, the way that I've drawn that. Why north of east and not east of north? Because my adjacent side is east. I'm going north of east up here. So I start out east and then I go north. If you'd drawn it differently, then your answer would be 25 newtons at 37 degrees east of north, which would be just as correct. If I want to find the equilibrant, now it's super easy because this is the one force to counteract this. How much would it be? Same amount of force, 25 newtons, and exactly 180 degrees pointing the opposite direction. So if I had an arrow, it would be the same size as this thing pointing the opposite direction. So it'd be something like that. That's 25 newtons at 53 degrees south of west. Okay. So I'll take that away. Hey, let's look at sample number 2. one of my favorite things is cheese. I know that's hard to tell looking at me, but I really like cheese. It's delicious. So assume a 10 Newton block O cheese is sitting on a hill and it's got a slope of 30 degrees from the horizontal, just like this. I want you to find the components or parts of the cheese's weight that are perpendicular to the hill. That's sometimes called a normal force in physics. Normal means perpendicular. And then the components that's parallel to the hill. Now, I want you to understand about this, again, first of all, I've got to draw a picture. So here's my picture. That's my hill, 30 degrees. Cheese is on the hill. And gravity is going to act straight down. So thanks to some miracle of geometry and similar triangles, since this is perpendicular to this surface, and this is parallel to this surface, and the Earth's gravitational pull is perpendicular to the ground, what I've drawn here is a similar triangle. And although the cheese's weight is 10 newtons, part of that weight is pushing into the hill, and part of that weight is acting to cause the cheese to slide down the hill. So these aren't two new additional forces. They're just splitting up this force into two parts, which might make it easier for us to think about things. And our next major topic of study is forces, so I can pretty much guarantee you that it'll help. So in this case, if I want to think about this side and this side, I can think about that the cosine of 30 degrees is, and this is again the 30-degree angle, just like this is the adjacent side divided by hypotenuse. So cosine of 30 degrees is equal to this normal component over 10 newtons, which is my hypotenuse. If I rearrange that, I can say that F normal equals 10 times the cosine of 30, which is about 8.67 newtons. If I want to find this parallel component, which would cause the cheese to slide down the hill, I do the same idea, or have the same idea, but since the trig function for this is opposite over hypotenuse, that's the sine of 30 degrees. So the parallel component is 10 times the sine of 30, which is 5.00 newtons. Now, I want you to think about extremes. So if this hill was completely flat, the normal force would equal the weight. In other words, all the cheese's gravitational pull would be pushing into the hill, and none would be causing it to slide down the hill, because there's no hill. As we get this steeper and steeper and steeper, the amount of the force pushing into the hill, or the normal force, will decrease, and the parallel component of the cheese's weight, or gravitational force, will increase. So if I have the extreme situation where my hill is completely vertical, I have no normal force, zero pushing into the hill because it's a vertical cliff, but all the cheese's gravitational pull would be acting parallel to the surface, which would cause it to accelerate down to the surface of the Earth, and that would be 10 newtons. Sample 3, and then I've got sample 4. So this is going to be a long screencast. Hopefully you don't watch it all at once. Get yourself a drink and a snack. A nice water, fruit juice, Coke, Cola, Classic, Sprite, something like that would be delicious. Milk, perhaps. Popcorn sounds good. All right, so here's number 3. This is a riverboat problem, and these are really typical physics problems because they involve relative motion. So there's a couple examples of these. So let's say you have a river, and it's 150 meters wide. Notice I've drawn it in blue. And it's got a current going downstream at 4 meters per second. So that's being drawn as south. Let's say that you have a swimmer who can swim 9 meters per second in still water, and that is ridiculously fast. That's like across our classroom in 1 second. So sorry about that. And they want to reach a pot of gold. And that's directly across the river in front of them, or directly across the river from them. Maybe there's mush down here, swamp downstream and upstream, so they just want to get to the pot of gold. So if they do that, hopefully you can recognize that they've got to aim upstream because the current's going to carry them back downstream. In this case, the resultant actually isn't the hypotenuse of the triangle, it's one of the legs of the triangle, because the person is going to aim upstream, that's where they're pointing, that's their 9 meters per second. And again, to get a resultant, we draw vectors tip to tail, so the current's going downstream, and so our resultant ends up going due east. So the question would be, where should the person aim to end up directly across from the start? Well, hopefully you recognize it's somewhere to the northeast. So, and I'm going to shrink this down so you can see a little more of it. So at this point, once I've drawn this triangle, and it would be really hard for me to do this without drawing the triangle, I need to figure out this angle. Well, this is the opposite side, and this is the hypotenuse. So that's the sine of the angle. So the sine of the angle is equal to opposite of hypotenuse, which is 4 over 9, which is 26.4 degrees. So the swimmer should aim 26.4 degrees upstream. Now it's asking for the resultant. In other words, if we were in a drone above the river and we looked at the swimmer, they might be trying to aim upstream, but the current's trying to carry them downstream. We would see the swimmer going directly across the river, which is kind of interesting. So like I said, it's a drone's eye view. In this particular case, then, we need to figure out this leg of the triangle. So I can use the Pythagorean Theorem and take my hypotenuse squared minus this side squared, and that would give me this side squared, and then I can take the square root of that. So 9 squared is 81, minus 4 squared, which is 36, gives me something around square root of 65, I think, and that's around 8.06 meters per second due east. The last question here would be how much time it takes to cross the river. Well, velocity, which is a vector quantity, is equal to displacement, which is a vector quantity, divided by time. So if I want to find the time, I can rearrange that. Multiply both sides of the equation by time. I get then time times velocity equals displacement. Then if I want to get time all itself, I divide both sides of the equation by velocity. I'm left with time is equal to displacement divided by velocity. And so seconds would equal meters divided by meters per second. So the units actually kind of work out there, because something in the denominator of a denominator is actually in the numerator. At any rate, when I do this, I get 150 meters divided by 8.06 meters per second gives me around 18.6 seconds for the swimmer to cross the river. Hopefully that kind of makes sense, because 150 meters divided by the speed should give you how long it takes to get somewhere. So just for example, if it's 100 miles from Pickerington to Cincinnati, Ohio, and I'm driving an average of 50 miles an hour, don't ask why I'd be going that slow, but 100 miles divided by 50 miles per hour would take 2 hours to get there. Maybe a combination of surface streets and freeways that might be close to 50 miles per hour. Here's the last example, and I would look at this one several times. So we're going to be doing some activities in class with this as well. So this is solving with a unit vector box. So I like to use north and east here, although I tend to like to also sometimes choose a dimension where I think most of my numbers are going to be positive. But for right now, I would always choose north and east. So if you have a vector that's not going north but south, that would be a negative value. If you have a vector that's going west but not east, that would be a negative value. So let's say we've got a person who's riding a bike and they're going 3 different legs of this bike trip. The first one is 23 kilometers due east, the second leg is 15 kilometers due south, and the third leg is 10 kilometers at 27 degrees north of east. Well, that's a little bit annoying. Sorry about that. So my sketch is the first one goes east, second one south, third one kind of northeast. If I'm going to guess, I'm going to kind of end up to the southeast. If I draw all these 3 tip to tail, and my vector resultant goes from the tail of the first one to the arrow tip of the last one. So now, when I do this, if I look at the first vector, and I put it in this unit vector box, none of it's going north. So that's easy, that's a 0. 23 kilometers is going east. I don't need to do any trigonometry, I can just look at that number. With this one, I've got 15 kilometers going south, but my unit vector box says north, so I'm going to put that as a negative 15 kilometers. And 0 kilometers is going east. But what about this mess? If I've got 10 kilometers going at 27 degrees north of east, I'm going to draw another picture. And that picture is only of this last vector. It's 10 kilometers, it's 27 degrees north of east, so east is the first leg of my triangle, and then I go up north. And what I need to do is solve for this east component and solve for the north component. So when I look at that, opposite over hypotenuse would be the north component, adjacent over hypotenuse is the east component. So sine of the angle is equal to the north component divided by 10 kilometers. Well, we know the angle is 27 degrees. So to get this north component all by itself, I multiply both sides by 10 kilometers, and it's 10 kilometers times the sine of 27, and that gets me 4.54 kilometers. And since it's north and my unit vector box is north, that's a positive. For this one, I do the same thing. East over 10 kilometers is equal to the cosine of the angle, adjacent over hypotenuse. So I can rearrange that and say that cos of 27 degrees is equal to east over 10 kilometers. Multiply both sides by 10 kilometers, I get 10 times the cosine of 27, and that equals 8.91 kilometers. And since this is east, and my unit vector box says east, that's positive. So when I add all these up, 0 minus 15 plus 4.54, I'll round that and get negative 10.5 kilometers north, 23 plus 0 plus 8.91, 31.9 kilometers east. So now I'm actually about 90% done, even though I don't have any of the answer yet. So now I'm going to draw a new triangle with the legs of the triangle from this T-chart or unit vector chart. And that's these amounts north and east. So I'm going to start east. I always tend to like to start with a longer leg of the triangle. So that's 31.9 kilometers. And then I've got negative north, so that's south. So I'm going to draw an arrow south of 10.5 kilometers. And then my resultant is connecting the tail of the first vector to the arrow tip or head of the last vector. So my resultant is going to be to the southeast. How much? I'm going to use Pythagorean Theorem, and I get 33.6 kilometers. If I want to get the angle is going to be equal to the tangent of 10.5 over 31.9 kilometers. So the tangent of this angle would equal that ratio. So to get the angle, you need to use the inverse trig function. That's inverse tangent, 10.5 divided by 31.9. That gets me 18 degrees. So when I look at my diagram, I could say that my overall resultant is 33.6 kilometers, and it's going 18 degrees south of east. East being my adjacent leg, and south being the second leg of that triangle. So hopefully those help. You can listen to this a couple times. Not that you want to listen to me, but it may help to have you understand how to solve vectors in addition to looking on the physics classroom.